This conference will now be recorded.
Hello everyone. Last day we have started isomerism, and some of the examples we have already seen under structural isomerism. Okay, there are two categories under when we are talking about isomerism in coordination compound. One is structural isomerism, another one is stereoisomerism. So coordination isomer that we are going to discuss now, that is the number 4 type under structural isomerism. And after finishing coordination isomer, structural isomerism will be complete, and then we will start stereoisomerism, and under which there is two more subcategories. Fine. So structural isomerism number 4 is the type is coordination isomer. Now from the term coordination isomer, that means it has something to do with coordination sphere, obviously. So this type of isomers arises in the coordination compounds where both cation and anion that will be present, both will be part of complex ion. That means it will remain in the within coordination sphere. And what will be how this isomerism will generate? There will be interchange of one or more ligands between the cationic sphere and the anionic sphere. Okay, or you can also say it is the exchange of metals. Both are fine, but it may be that the metals are same in both cationic sphere and anionic sphere, or it may be that they are different. Okay, that is, in cationic sphere we have one metal, and anionic sphere we have another metal. So here the example that we are seeing, it is zinc associated with 4 ammonia. It is carrying 2+ charge. That means zinc is having 2+ oxidation state here, and this is the cationic part, which is complex ion, and the anionic part, that is UCl4 2-. Now Cl is anionic ligand. It is carrying total 4 negative charge, and outside extra charge is 2-. That means oxidation state of copper, that is also 2. Now when there is exchange going on, that is copper is taking the place of Zn and Zn coming towards copper, then you are getting a new isomer. Or you can also say that ammonia is going from Zn towards copper. Both are actually same thing, whatever we say. So now we are getting and the coordination isomer. Now in the cationic part we have copper. Oxidation state is same, there is obviously no change. But now in anionic sphere there is Zn. Okay, some more examples we will see. CO ammonia 6, then CrCN6. Now ammonia is neutral ligand, okay, and Cn is anionic ligand. Fine. So here we have oxidation state 3, which is also 3. Now chromium carrying positive charge 3, and there are 6 ionoligand. That means 3 negative charge will be present outside the coordination sphere. And in the left hand side cationic part, ammonia is neutral, so outside the coordination sphere there will be 3+ charge. Fine. Now if you write the full structure, it will be something like this. This is the cationic part and this is the anionic part. So this is one isomer and its coordination isomer. Now what will happen? Now cobalt, just place it here, and the position of chromium, now it is going towards this. Okay, now in the cationic part we have chromium, oxidation state there is no change, and in the anionic part there is cobalt. Fine. So these two are also examples of coordination isomer. Two more examples we are going to see. Now here we have same metal. These two examples that you have just seen, zinc, copper, cobalt, chromium, we have seen two different metal, but now metal may be also same. So this is the first isomer where chromium, it is with 6 ammonia, and then in the anionic part chromium is with 6 thiocyanate. Now see, if some of the ammonia ligand, it is going towards this, that is 4 ammonia ligand, it is now moving from one coordination sphere to the anionic coordination sphere, and 2 SCN, only 2 SCN, and 4 ammonia, sorry, is CN2 ammonia 4. Okay, so here we have 2 SCN and 2 ammonia, it is now here. So that is why From 6 SCN now it is reduced to 4 SCN, and there is no ammonia before, but now there are 2 ammonia. But coordination number is same because it is 2 and 4. This is also 4 and 2. So it is 6. That is octahedral complex. Fine. And the other example, here also we have just, in this example, we have seen cobalt and chromium. Here also it is cobalt and chromium. Cationic sphere it is with 6 ammonia, and chromium in the anionic sphere with 3 oxalate. Now oxalate it is bidentate ligand, so that is why to fulfill 6 coordination 3 oxalate ligand fine. Okay. And when it is a second isomer, now chromium is here, cobalt is here. Fine. So in this coordination isomer, we have seen different examples. Now after finishing structural isomerism, there are total 4 categories. 3 of them we have discussed in the last class. Today we have discussed one of them, that is the last one, which is coordination isomer. After finishing it, next is stereoisomerism. Now in case of structural isomerism, the main important point that we have seen is the bonding connectivity, that is same. There is no change. Okay. But now stereoisomerism, sorry, what I have said, bonding connectivity is different. But now what will happen? Bonding connectivity will remain same, but there will be some change in the 3-dimensional arrangement. So that is why the name is stereoisomerism. So obviously chemical formula is same because that is the definition of isomer, and connectivity between the central metal atom and ligands, that is also same. So where is the difference? The difference is in the spatial arrangement or 3-dimensional arrangement of atoms, and based on these we can have 2 more types under this category, that is under stereoisomerism. We can have geometrical isomers and optical isomers. First we will discuss geometrical isomers, and after finishing this there will be optical isomers. Okay. So what is geometric isomerism? Isomerism which occurs because of different relative arrangement of ligands around the central metal atom, and that is known as geometrical isomerism. Now it is present in square planar when it is 4 coordination, and octahedral when it is 6 coordination. But in tetrahedral isomers, geometrical isomerism normally we cannot see, though there are some exceptional cases, but mostly if it is tetrahedral geometrical isomerism, not possible. And why it is not possible, that also we will see. But try to understand that what is geometrical isomerism? Different relative arrangement of ligands around the central metal. So it will be clear with more examples, but before that we will discuss this question, that why geometrical isomerism not possible in tetrahedral complexes when you have 2 different types of unidentate ligand coordinated with the central metal. Because if it is at least 2 different ligand must be present. Suppose if I am saying that it is MA4, so all the ligands are similar type, so obviously isomerism not possible. But suppose if the formula is MA2B2 in case of tetrahedral, then also it is not possible. Now why it is so, that we are going to see. So when it is tetrahedral arrangement, see, this is tetrahedral arrangement, and here the angles are 109. So here we have 2 green colored sphere and 2 orange colored sphere, and the pink one, that is actually the metal. Fine. Now in tetrahedral geometry, the standard angle, what we know, it is 109 degree. That means only one type of angle is present. So whatever 2 atoms you consider that are attached to metal, they will always get the same angle. So this is 109 degree, this is also 109 degree, this is 109 degree, so all are 109 degree. So under this condition, if you exchange any of these 2, so you will get the same arrangement, because after all our angles are same. Okay, so that is the reason it has no geometrical isomerism, because all the bond angles are same. Bond angles are same. Okay, for geometrical isomerism, at least one bond angle should be different, otherwise you cannot get geometrical isomers. Okay, because orientation will not be different so that it can show isomers. Now if you consider square planar, see the second picture is for square planar. So when the square planar arrangements containing same type of atoms, so it is the type of Ma2B2. Suppose this is green color and this is the orange one. Okay, now see, two types of angles are there. If you consider these two green one, the angle is 180. But if you consider this or this, now it is 90 degree. That means two different types of angles are there. Now if the two same ligands, suppose the green, if they are present 180 degree apart from each other, you will get one isomer. If they are 90 degree to each other, you will get another isomer. Okay, so in the first one, as they are 180 degree both with respect to the orange one and the green one, so that is why it is known as trans, and this is cis. Okay, but this type of arrangement, two different arrangement is not possible in tetrahedral geometry because there all the angles are same. So this is the reason why geometrical isomerism is not possible in tetrahedral complexes. Geometrical isomerism with coordination number 4 under this category, first we will see different types. So complex of type MA4, that means all the 4 ligands are same. Then 3 ligands same, 1 different. A3B or MAB3, whatever, same actually. They do not show geometrical isomerism. And obviously from the formula it is clear that here A and B are monodentate ligands. So if you have this type of formula, coordination number 4, there will be no geometrical isomerism possible. Okay. Now if we consider the next formula Ma2B2 and Ma2BC type of isomer, ABC obviously all are monodentate ligand. Now they can have two different type of geometrical isomer. So see, when it is Ma2B2, here examples we have taken platinum, 2 chlorine, 2 ammonia. This is the example of Ma2B2. Now here both, that is same ligand, it can remain on the same side or 180 degree, that is 90 degree and 180 degree. So when it is 90 degree it is cis, when it is 180 degree it is trans. Next type is Ma2BC. Now PT, A is ammonia because it is 2 A ligand, and B and C, suppose this is B, this is C. Now here also, what is the difference with the previous one? Previous one you have just 2 types of ligand, now you have 3 types of ligand. But see here A same, so this same ligand when they are 90 degree it is cis, but when it is 180 degree it is trans, so that is why 2 types possible. Now come to the third point, complexes of formula MXY2. Now here XY is unsymmetrical bidentate ligand. So unsymmetrical bidentate ligand, very good example here we have taken glycine, that is CO, O minus, and in this side we have NH2. Basically glycine is the simplest amino acid. Formula is NH2, CH2, CO2H. But here we have removed the acidic proton. So these two will be the donating site. Okay. So as here it is bidentate ligand. So two ligands are enough to show this cis-trans isomers. So XY is unsymmetrical bidentate ligand. So as it is unsymmetrical bidentate ligand, so as if it is behaving similarly, just like this. Only difference is now it is attached. That is this N terminal and on terminal, these two are attached. That is the only difference. Otherwise, it is behaving same. So two similar coordination site when it is 90 degree to each other, it is cis, but here they are 180 degree. Okay. And the fourth possibility, complex of formula ABCD. Now all the 4 ligands are different. So we have total 4 different types of ligand. Here we have taken example PT, Cl, NO2, Br, and ammonia. So this is of type MABCD. Okay. So here, remember, three isomeric forms are possible. So these are the three possibilities that are written here. If you can also try or explore and draw other isomers, but you will see you cannot get more than three. So for MABCD type in square planar geometry, maximum three geometric isomerism possible. Okay. Now, after finishing 4, what happens with coordination number 6? So when it is coordination number 6, complexes of type MA6, that means all are same ligand, or 5 same, 1 different. Now for these two formulas, geometrical isomerism in octahedral geometry not possible. Now the next type, MA4B2 or MA4BC. So this is MA4B2, MA4B2, both are MA4B2, but these two actually will behave similarly. Okay, so see what type of isomers we are getting here. Here 2B same, so when it is 90° to each other, these two are actually same. See, there is equal sign given. Okay, so it will be C's. So both these first two picture, it is the picture of C's, but when they are 180°. So whenever any complex is given, you have to check what is the angle, and according to that you can understand C's or trans. So it is 180°, this is also 180°. So it is not important that whether this BMB, it is vertical or horizontal, that is not important. What you have to see is that whether they are in this having, what is the angle between them, that is the important thing. Okay, because sometimes this B, it may be in the square plane directly, but it may not be always. And actually see, though we are here, we have this blue marked area which is square plane, but this is also another square plane, right, where this will be serving as vertical. So just rotate it, it will be like this. That is the second one. So just check the angle between two same ligand, and if in one B is replaced by C, then also it will be same thing. Okay, so MA4B2 and MA4BC, they can have two geometric isomer. Complexes of time MA3B3, so three similar ligand, then other second type of ligand, that is also total 3, exist in two geometrical forms. Now the name is different, it is not cis trans. Now we are using a new term which is facial, in short FAC, or meridional, in short MER, that is FAC and MER complex. When three ligands of the same time and arranged in one triangular face, then the isomer will be facial. So facial means what? The three same ligands must remain in a triangular face. So this is the FAC isomer, and if you join all the 3B, the triangle that you are getting, that is actually a face of a triangle, right? Similarly, you can also join the 3A atoms. There will be formation of a triangle which is away from us, not towards us, but still it is a triangular face. But what is meridional? Now see the arrangement in the second case, which is meridional example. Here also you are getting a triangle, that is 5, but it is not on the face of the octahedral, because in octahedral there are different octahedral, in octahedral geometry there are different triangular face. But this triangular arrangement that you are getting, that is actually inside the octahedral, right? You can also join the 3A, similar type of thing will happen. Okay, so depending on what type of arrangement is there, it will be either facial or meridional. Okay, now here we have MA4BC. Okay, it is example of MA4BC. Why we are calling it Cs? Because these all are C, 90°, 90°. Actually, with respect to A, here we are not considering whether it is Cs or trans. Okay, Here we are considering it with respect to B and C. So as if it is 2B or 2C, we have replaced one B or C with another atom. So that is why B and C here it is 90 degree, but here it is 180. Okay. And here we have the actual example of this type, that is PT 4 ammonia, that means 4A. Suppose all these are A. This is B, this is C. Okay. So this is a general example and this is the actual example. Okay. Some more types we will see. Complex of formula MAB. Now see, we have taken bidentate ligand. In the previous slide, we have not used any bidentate ligand. All the examples are monodentate ligand. But what if we have taken bidentate ligand? So here capital AB, that is actually the bidentate ligand, and small BCD, they are monodentate ligand. And when I am saying AB capital, that means it is not just bidentate but also unsymmetrical. So that is why it is AB. If it is capital AA, then it is symmetrical bidentate. Okay. So if you have this type, and here coordination number is 6 because 2 you are getting from AB because it is bidentate. Then 2 you are getting from monodentate B, then 1 from C, 1 from D. So it is 6. Now here we can have total 4 type of Cs. Now that is AB, it will always take Cis position because the length between A and B, it is not so high that it can be arranged in 180 degree arrangement. So it will always be Cis. So this part is common. See, it is always 90 degree. So just focus on the 2B ligand. It is 90 degree, 90 degree, B 90 degree. This is also 90 degree. But 4 possibilities are there. You will not see that any of these 4 are actually same. But if it is when we are saying it is trans, still this part is common because we cannot make any change here. You cannot place A and B in trans position. That is not possible because the length is not so high. Now B 180 degree to each other, again 180 degree to each other. Okay, so 2 trans and 4 Cs, fine. Next type Ma2B2C2. So all are monodentate ligand. 3 different types of monodentate ligands we have taken. There are total 5 possible geometrical isomerism. Okay. Now how you will write it? See, it seems difficult, but it actually not. What you will do when we are saying that A trans means here A is trans to each other. So obviously C and B, it will be, you have to keep it Cis. Okay. So only A trans. Similarly, only B trans. But see, AA or CC, they are 90 degree. Only B trans. Only A trans, B trans, C trans. But A 90 degree, B 90 degree, CC 90 degree, BB 90 degree. Now other possibilities, all are trans. That means C 180 degree, 180 degree, 180 degree. Okay. And the another possibility, all C's. 90 degree, 90 degree, 90 degree. Fine. Now, very unique example, A, B, C, D, E, F. 6 different types of ligands are present. Though this is not very common, but still you should know it because it is a very good example. Now, whenever you will have this type of ligand, it is not really not possible to draw all of them, but you just have to memorize it, that it may exist in 15 isomeric forms. Okay. And under this category, actually only one compound identified so far. So it is not that you have so many examples of this type. No, that is not the case. Only one type is reported until now, and the type is C. PT is the metal here, and we have 6 different types of ligands. bromide, chloride, iodide, 3 halogen, then nitrite, ammonia, PDD. Okay, so whenever you will have this type, it is not just for this. If there is any other, though other example is not present, this is the only example, but this type of general formula can be given in the question, and it can be asked that how many geometric isomerism possible. So it is 50. Fine. Complexes of formula MAA2B2. Now AA2 means capital A, so it is here bidentate ligand, and it is symmetrical bidentate ligand. Though monodentate ligand I should take small b, but as in the example, the picture, it is using capital B, so to match with this I have given capital B also. But normally monodentate ligand we use small letter. Okay, so either AA2B2 or AA2BC. So we have two symmetrical bidentate ligand. That means per ligand two coordination site. So if it is two symmetrical bidentate ligand, it will be serving 4 coordination sites. So two coordination site left, there will be 2B or 1V and 1C. So here what type of isomerism we are getting? See, the symmetric ligand, it will always be 90. As I have said, it is the length between the two coordination site, it is not so high, it can take 180-degree arrangement. So it is always 90 degree. But you have to focus on what about arrangement of B. So B, they are having 90-degree angle between them, but here it is having 180-degree angle between them. So that is it is trans. And here we have taken the example cobalt En2 Cl2 plus. So cobalt is here M, En is AA, and Cl2 is B2. Okay. Now next type MAB3. So again AB means unsymmetrical bidentate ligand. Now it is also forming two types of geometric isomerism, and here you will see in some books it is using the term cis, sometimes it is using the term fac or trans or mar, but I will suggest that it is better to use the term fac and mar. Okay, so I have here this general formula and the corresponding picture MAB3. Now it is cis form means, see here when we are saying bidentate ligand, it has to be cis, because if you simply consider this angle between AB, in both the cases it is cis. Then why we are saying that it is cis? We are saying it is cis because if you focus on same atom, that is a coordination site same, their arrangement is cis to each other. Fine. And in the trans, here at least one AA, they will be 180-degree to each other, and one BB 180-degree to each other. But in the cis form, you will never get it. But it is always better you use the term facial and meridional in these cases, because when you are joining these 3B, you are getting a triangular face. So that is why it is facial. And if you are joining 3B in the second picture, now you are getting a triangular face also, but it is not face actually. It is triangular in shape, but not face. It is inside the octahedral geometry. So that is why it is meridional. Okay. Though sometimes cis terms also used. Now actual example, if we see chromium, which is the metal, here the bidentate ligand, unsymmetrical bidentate ligand that we have taken is chromium GLY whole 3. GLY means glycineto, that is CO2H, CH2, NH2, simplest amino acid. So here how it is serving bidentate ligand, because the acidic hydrogen if we remove, it will now serve as bidentate ligand. Okay, so one site is N, another one is O. So if you join all the N or if you join all the O, you are getting a triangular face of octahedral geometry. But in the second case, if you join all the oxygen, you can also join all the nitrogen. Now see, now here also we are getting triangular arrangement, but it is not on the any of the face, it is inside. Fine. So here AB is unsymmetrical bidentate ligand. Example we have taken glycineto ligand. So under stereo isomerism, one is finished, which is geometrical isomerism, and one is left, which is optical isomerism. Compounds which can rotate on the plane of polarized light, which can rotate the plane of polarized light, will be called optically active. Now, to understand the meaning of the statement, you have to know what is plane polarized light. We can understand that compounds which can rotate a particular type of light, but what is plane polarized light? Okay, that we have to know first, then only we can understand how we are getting optical activity. So in this picture, as you can see, in the left hand side, three different colors wavelengths are there: blue, orange, and green. Okay, so there is mixed of wavelength, and different wavelength, they are having different plane. They are not, though it is two-dimensional, it is a screen of the computer, you cannot understand, but you have to imagine it that it is in the three-dimensional arrangement, not the planes of all these three wavelengths are same. You can see the green one, that is actually as if perpendicular to the plane of the screen. Okay, and the orange one, that is directly on the screen, and blue, that is in between. But so this type of light, when there is no fixed plane, it is different mixed of plane are there, it will be unpolarized light. But there is a particular type of polarization filter. Details we don't need to know. Just see, when there is polarization filter with vertical passage. Now vertical passage means only the orange color wavelength it can orange colored wave it can pass through, not the other one. So that is why now we are saying it is vertical passage. So it is as if filtering some from the mixture. Now you are getting only one. So the single wave that you are now getting, it will be called linear polarized light only with one plane of oscillation, because now mixed oscillation plane is not present. Okay, so that is all about plane polarized light. This much information is enough. So this type of light that you are seeing, that is in the right hand side, after passing through the filter, suppose you have taken this type of light and you have taken also a solution of optically active compound. So when the light will be passing through this compound, what will happen? There will be rotation of this plane. So now it is having a particular plane, but after passing through the optically active compound solution, the plane will change. And what will be the rotation angle? That depends on the compound, obviously. Okay, different compound, different rotation angle. So this is all about plane polarized light, and compounds which can rotate this type of light, they will be called optically active. Now, the two forms of optical isomer. Isomer means always it is a pair. Fine. So one isomer of this pair will be called dextro, in short small d. Do not use capital D, that is completely different thing. Here dextro, use small d, or levo L. So how we will understand which one is dextro? It depends on whether optically active compound solution, it is rotating this type of plane polarized light to the right hand side or to the left hand side. So depending on whether it is moving it or rotating it clockwise or anti-clockwise, two different types we can get. And remember left L, so L, you can remember it in this way. Now if in a solution, suppose dextro and levo both are present equimolar, that means same number of moles, or you can say same percentage you have taken, then what will happen? One will rotate the plane polarized light to a particular angle, suppose x degree, to the right hand side, but the other one, as it is present in the same exact amount, it will also rotate it to the same numerical value, but now in the opposite direction. So that is why it will cancel each other, and ultimately it will behave as if it is not optically active. Okay, so if the equimolar mixture, it is optically inactive. Actually optical activity is nullified by each other. It is not optically inactive, but as you have taken equimolar amount, so that is why it is now, it has become optically inactive, and this is known as racemic mixture. The pair of two optically active isomer, which are they are actually having mirror image to each other, they are also known as enantiomer. And this type of isomers, if we try to superimpose, it is actually non-possible. Okay, so non-superimposable. So very good example, if we take our left hand and this is right hand. Okay, now directly if you try to superimpose, it is not possible. Okay, because suppose if it is left hand, though here the left hand is towards us, but suppose if you have placed it somewhere where this is the thumb, okay, and in the right hand side the thumb will be like this, so the thumbs are facing to each other. Now when you are trying to superimpose on it, what will happen? Now the thumb will be this side and the left hand side thumb will be this side, so it is not superimposable. Okay, that is I'm trying to show here. But when you have taken the mirror image of the right hand, now it looks like the left hand. So that is why it says the mirror image relationship is present between them. Fine. Now actual example if we take. So here we have taken one coordination compound. What compound we have taken? Cobalt En2Cl2. So we have taken this coordination compound. Okay. Now these 2Cl, when it is 180° to each other, that means it is trans. Fine. So the trans isomer, and if you look at its mirror image, they are actually same. Okay, so we cannot call them that they are enantiomer to each other. And also if you are having trouble to understand mirror image, another way also you can understand that in this molecule that is trans, it is not behaving as optically active because here we have symmetry plane present. So where is the symmetry plane? The symmetry plane is this square plane itself. If you cut the molecule along this plane, both are same. Okay, so whenever you have this type of symmetry sigma plane, it will not behave as optically active compound, and you will see mirror image will also be identical. But the same molecule, if the 2Cl are now 90° to each other, so now it will be cis. So when it is cis, suppose it is isomer number 1, here 2 chlorine, they are cis. Actually cis it is with respect to 2 chlorine, because En it will always be cis, it has to be. Now this is isomer 1. Okay, and isomer 2 has the same structure as the mirror image of isomer 1. So suppose it is 1, it is 2. Actually these two are related to each other as enantiomer. One of them will be D, another one will be L. But when you have taken the mirror image of isomer 1, okay, now it looks same, right? So directly it is not looking same, but when you have taken its mirror image, so these two are looking same. Okay, so isomer 2, it has the same structure as the mirror image of isomer 1, and also isomer 2 cannot be superimposed exactly on isomer 1. So we cannot say they are identical, but if you do it for trans, you can superimpose. So that is why the cis is optically active, but not the trans one. And geometric isomerism we have already seen. And now we are using these terms cis and trans, which are basically the terms for geometric isomers. So as we already know now what is geometrical isomerism, so after this slide when we will discuss optical isomerism, basically most of the time you will see we are using the term cis and trans first, and then we are trying to see whether this particular geometrical isomerism it has some optical activity or not. So here you can see here cis trans is possible for this complex compound, but only the cis is optically active. Trans is optically inactive. Okay, that means from cis now you will get two isomer D and L, or you can say enantiomer, but from T you are getting only one. So if we are saying that, if the question is asked that for this particular complex how many stereoisomers possible, then the answer will be it is 3. And if it is asked how many geometrical isomerism possible, answer will be 2, only cis and trans. If it is asked how many optical isomer possible, it is basically 2, which is generated from C. Okay, so geometrical isomer 2 possible, but cis is giving you D and L, so that is why ultimately it is 3. Because when we are considering stereoisomer, you have to consider both, because this is in the subcategory of stereoisomer. Fine. So whenever question is asked that find total number of stereoisomer, be very careful what it is actually asking. If it is asking stereoisomer, then different answer. Or it is asking how many geometrical isomer or how many optical isomer. So all these are not same question, okay, different. Though sometimes it may be that there is no optical activity shown by any of these cis or trans. It may be in some cases. Then it will be 2 under stereoisomer, 2 under geometrical isomer, and optical isomer it will be 0. Okay. Optical isomerism in complexes with coordination number 4. Now when we are saying coordination number 4, it may be tetrahedral, it may be square planar. So first we are seeing what about tetrahedral, what happens here. So for tetrahedral complex type MA4, all are same, then A3B or AB3. Optical isomerism is possible, not possible, because all the possible arrangement of the ligands round the central metal ion are exactly equivalent. Fine. Now this you have also seen when we have discussed geometrical isomerism in case of square planar. When it is MABCD, it seems at a first glance that now it is optical activity possible. Actually here also it is possible, but what happens actually, theoretically it is obviously possible because of the labile nature. Labile nature means, suppose we have M, A, B, C, D, and if you have taken its mirror image, so these two are obviously optically active and related to each other by inertia. So suppose this is D and there is L also. But what happens, because of their labile nature means the ligands, they can change their position very quickly. So what will happen now, D can be converted to L and L can also be converted to D. So there will be an equilibrium. So ultimately it is their positions are not fixed, they are changing each moment. So that is why after all it will be mixture of D and L, and here we cannot resolve it. Fine. So though it is theoretically possible, but practically it is not optically active. But if you have tetrahedral complex where unsymmetrical bidentate ligands are present, then you can expect optical activity. Okay. Example, here beryllium complex we have taken. Now this beryllium, we know it is from group 2, that is alkaline earth metal. But with beryllium, this type of complexes are common. So for showing example, we have taken this. So here the ligands that you are seeing, it is bidentate, but it is not symmetrical. It is unsymmetrical. And what is this ligand? If you look at the ligand carefully, it is actually PH, CO, then CC double bond, then O. It is actually O minus, then Me. Now, actually it is OH. Now see, it looks like enol. Fine. So basically, if you consider that is tautomerism and what is the keto form, the keto form is like this. Diketo compound, 1,3 diketo compound, because 1, 2, 3 at 1 and 3 position there is 1, 2 keto group, so that is why it is 1,3 diketo compound. And enolization is possible. So after enol formation, you are getting this type of structure, and here just remove this H, you will be getting a negative charge. So now it can bind to metal. It is behaving as bidentate ligand, but it is unsymmetrical because this side and this side not same. Okay, and it is tetrahedral arrangement. So all these angles that you are seeing, all these are 109 degree, and when you have taken its mirror image, you are getting another isomer. So these two are enantiomer. Fine. But if it is identical group both side, that is symmetrical bidentate. Now both side, again you have taken enol type, but both side now same. In the previous case it is pH and Me, but now both are Me. So now optical activity not possible, it is occurring. Okay, so it must be unsymmetrical. If it is symmetrical, it will not work. Fine. Coordination number 4, but now it is square planar geometry, not tetrahedral. Now what will happen under this condition? Square planar complexes are generally achiral. The reason is the molecular plane of the complex, it itself acts as a plane of symmetry. So very simple example, suppose you have platinum, there is 2 chlorine, 2 ammonia. Now this is a perfect plane, right? So if you have this type of complex here, optical isomerism not possible because the plane itself is acting as a symmetry plane, the molecular plane. Okay, molecular plane means the plane which is existing in the molecule itself, considering all that. So therefore it doesn't show optical isomerism, but it is possible if you have taken some special kind of ligand. So what is the special kind of ligand? Under two cases it can show isomerism, though that is rare and you will hardly see any example, but still you should know it. Optical isomerism may also appear in square planar complexes if you have asymmetric ligand. First case, second case is specially chosen bidentate ligand. So first we will see if you have taken asymmetric ligand, what will happen. So what asymmetric ligand we have taken? See here the ligand to nitro monorated, that is fine. But here important thing is in the left hand side ligand. So this ligand, it is like this, CO, O minus, then CH2, N, Me, Et. Okay. Now this nitrogen center, it is actually chiral center because you have all the 3 different groups. Fine. So that is why in the previous case, that is in this complex, if you cut the molecule, it is actually the same plane. But now if you cut the molecule along this plane, the half, if you consider this plane on the plane of the screen of the computer, then obviously this CH2 which is in bold bond, that is towards us, and this methyl which is away from us, and this C2H5, this is directly on the plane. So when you are cutting the molecule along this plane, both have not equal because in this half which is towards us, there is CH2 CO2 minus, but the other half which is away from us behind the screen, there you have methyl. So both half are not equal. So that is why when you have chiral bidentate ligand, then square planar complex will show optical activity. Next, specially chosen bidentate ligand. Now what is specially chosen bidentate ligand? What we have taken here? If you look at the ligand, you will not find any chiral center. This is not chiral center because you have 2 same group, and this is CH2. And terminal position, we have 2 NH2. So this is bidentate ligand. So this is achiral bidentate ligand. But still, see what is happening. In the left hand side ligand, there are 2 methyl groups. In the right hand side ligand, you have HH on one side and PH on the other side. Now just join all these 4 nitrogen and PT. So if you cut the molecule along this plane, one half there will be presence of 1 methyl and these 2 H, and another half there will be another methyl and these 2 PH. So though the individual ligands, we have taken basically 2 different types of ligands, left hand side one type, right hand side other type. So though the ligands are not chiral, but still it is taken in such a way, it is a special case that you can have optical activity. But see, here it is achiral tetrahedral. Okay, because now the pH, that is in this arrangement both the pH are on the same side. Fine, but now that is not the case. So that is why it is achiral tetrahedral. So these two ligands are not same. Here both the pH are on the same side. Here they are not on the same side. Okay. Optical isomerism we have seen in case of coordination number 4, and under coordination number 4 we have square planar and also tetrahedral. Fine. Now if the coordination number is 6, that is octahedral arrangement. So when it is complex, different types now we are going to see. The first type we have taken MA4B2. It can exist in Cs and transform, that we have seen in geometrical isomerism slide, right? Because cis trans, when we are using, it has nothing to do with optical isomerism. It is all about GI, geometrical isomerism. So this can show these two types of GI, but both these forms are optically inactive. Okay, so for this type of complex, you will have one cis and one trans, but zero optical isomer. So that is why if it is asked how many geometrical isomers are possible for this complex, answer is 2. And if it is asked how many stereoisomers are possible, that is also 2, because there is no contribution from optical isomers. Okay, and why both of them are optically inactive? Because of plane of symmetry. So just take this example, suppose MA. So first I am drawing the trans one, and this is cis. Now under this condition, the first one is trans, this is cis. Now if you cut the molecule along this plane, both sides are equal, so there is plane of symmetry present. And in the second case also, if you cut the molecule along this plane, or you can also cut the molecule, yes, this one, then also see both half you are getting A. So that is why in both cases there is plane of symmetry present. Actually, sometimes you may get more than one plane of symmetry, but to be optically inactive, just one plane of symmetry is enough. So if you are finding just one plane of symmetry, you don't have to search for any second or third. One is enough so that you can say it is optically inactive. If it is type MA3B3, exist in facial and meridional forms. Obviously for this type we have seen that FAC and MAR isomer possible when we have discussed geometrical isomerism. But now individually if we consider this geometrical isomerism, they are also optically inactive. And why it is so? Because again the same reason, that there is plane of symmetry present. Fine. So here if we join these 4 in the meridional isomer, now if you cut the molecule along this, you will see in both sides what you are getting. In both sides you are getting AA, that means plane of symmetry is present. Okay, so just draw the geometrical isomerism proper structure and then try to find out whether any plane of symmetry is present or not, because it is not always possible that you will take the mirror image and try to see superimposable or not. It is comparatively difficult. My suggestion will be just draw the isomer and try to find out whether any symmetry element, that is plane of symmetry, present or not. So if plane of symmetry is not present, so it will be optically active. But in this case, plane of symmetry present, so that is it is not possible. Complexes of formula Ma2B2C2. Remember, this type we have already discussed in case of geometrical isomer. right? And then we have already seen 5 types of possible, where only A trans, then only B trans, and only C trans. This is all trans, this is all cis. So 5 GI possible, but out of this 5 GI, out of which only all cis form is optically active. So you are getting 5 GI. Out of this 5 GI, only one is showing optical activity. That means it will have one more isomer. So ultimately, total stereoisomer will be 6, but geometrical isomerism is 5. Okay. So this form is not, this form is only optically active, because in this form you will not find any symmetry element. If you consider the others, in each case you will find some symmetry element. See, when it is A trans, if you cut the molecule along this plane, both half equal. Then in this case, if you cut the molecule in this plane, it is both side B. Then here both sides C. Fine. When it is all trans, then also if you cut the molecule along this plane, both side A. But this type of symmetry plane, that is not possible in case of all cis form. Fine. So that is why we are getting only optical activity only from the all cis form. So some more examples we will see for optical isomerism in the next class. Today we are ending the session here. Thank you for listening.